In this video, we're going to talk about positive definite matrices. Positive definite matrices are a particular kind of symmetric matrix. And in this video, we're mostly going to stick to 2 by 2 matrices. So let's give the definition. A symmetric matrix. Remember, a symmetric matrix is a square matrix whose transpose is equal to itself. A symmetric matrix is called positive definite. If all of its eigenvalues are positive. And it's called negative definite if all of its eigenvalues are negative. Now, if your matrix, your symmetric matrix, has both positive eigenvalues and negative eigenvalues, the matrix is called indefinite. So it's indefinite if it has at least one positive eigenvalue and one negative eigenvalue. So that's the definition. Now it's possible that you have a symmetric matrix that's neither positive definite, negative definite, nor indefinite. So for instance, if you have this matrix like this, right, this matrix has eigenvalues 2 and 0. This is a diagonal matrix. And it's neither positive definite, negative definite, nor is it indefinite. It's not indefinite either because it doesn't have any negative eigenvalues. And in this video, so such a matrix is not invertible. And in this video, we're going to stick with invertible matrices, so we're going to ignore what happens when you have eigenvalue 0. So let's take a look at an example. Let's say that you take this matrix (1, -4, -4, -5). It turns out that it has eigenvalues (3 and -7. So A is what? It's indefinite. Okay? Now, just because a matrix has positive entries, if you have a matrix that has positive entries, it might not be positive definite. So a matrix with all positive entries is called a positive matrix, but what we're talking about is positive definite matrices. Those are different. So let's see if we take the matrix A, which is like this. This has all positive entries, but if you look at the eigenvalues, the characteristic polynomial is what? It's lambda squared minus the trace, that's minus 4 lambda, plus the determinant. which is 3 minus 4 is negative 1. And if you set this equal to 0, then lambda is going to be, by the quadratic formula, 4 plus or minus the square root of b squared, that's 16, minus 4ac. That's negative 4 over 2a. So this is going to be 4 plus or minus the square root of 20 over 2. That's 4 plus or minus 2 root 5 over 2. And that's going to be 2 plus or minus root 5. So the eigenvalues are lambda 1, which is 2 plus root 5, and lambda 2, which is 2 minus root 5. And root 5 is bigger than 2, so lambda 1 is greater than 0, lambda 2 is negative, and so therefore this matrix is actually indefinite. Also, even though all of its entries are positive. Okay, so you can't tell whether a matrix is positive definite or negative definite just by looking at the entries of the matrix. By the way, how is the notion of positive definite related to quadratic forms? If A is a positive definite matrix, one thing we've seen is that when you take the quadratic form, which is z of x1, x2, and let's just stick to 2 by 2 matrices in this video, you take the quadratic form x1, x2 times A times this column vector x1, x2. This is going to look like a bowl when you graph it. It's going to have this bowl-like shape. And the point 0, 0 is a minimum. Okay. If A is a negative definite matrix, then what happens is the corresponding quadratic form, which we defined above, this, so here's the graph of z1, z of x1, x2. Okay, this is the x1 axis, that's the x2 axis, this is the z axis. When A is a negative definite matrix, the graph is going to be like this. So here's the x1, x2, and z axes. The point 0, 0 is a maximum. This is a review of what we've talked about before. And if A is indefinite, it has a positive and negative eigenvalue, then your graph is going to look like a saddle. It's going to look something like this. And the point, this point 0, 0 is a saddle point. So we get an idea of what the quadratic form looks like by knowing if A is positive definite, negative definite, or indefinite. And to review why this is true, go back to the video on quadratic forms and symmetric matrices. The idea is that if you have a positive definite matrix, then after a change of variables, this is going to be lambda 1 u1 squared plus lambda 2 u2 squared, where lambda 1 and lambda 2 are both positive. And in that case, you're going to get a bowl. If you have something like this, where A is negative definite, well, then you're going to get something. After a change of variables, it will still have the form lambda 1 u1 squared plus lambda 2 u2 squared. But if the eigenvalues lambda 1 and lambda 2 are negative, the graph is going to be this downward pointing bowl. And if A is indefinite, then basically you're going to have something of the form lambda 1 u1 squared plus lambda 2 u2 squared, where one of lambda is positive and the other lambda is negative. So lambda 1 is positive and lambda 2 is negative, or lambda 1 is negative and lambda 2 is positive. And in that case, if you go in the u1 direction, the graph is going to go up or down depending on the sign of lambda, and then if you go in the u2 direction, then the graph is going to go up or down depending on the sign of lambda 2. And if they have different signs, then that means that in one direction the graph is going up and in the other direction it's going down, and that means that the point 0, 0 is a saddle point. Alright, so let's take a look at how to tell if a matrix, well, we're going to stick to a 2 by 2 matrix, is positive definite, negative definite, or indefinite, without finding the eigenvalues. Of course, for a 2 by 2 matrix, it's not hard to find the eigenvalues because you can just use the quadratic formula. But we'll find a criterion that makes it a lot easier. So we're going to stick to invertible matrices. Well, our symmetric matrix is going to have the form A, B, B, D, right? And let's say that lambda 1 and lambda 2 are the eigenvalues of A. Well, the characteristic polynomial is going to be, it's the determinant of A minus lambda I, and the lambda 1 and lambda 2 are the roots, and so you can factor this as lambda minus lambda 1 times lambda minus lambda 2. Okay? So this is a polynomial, and when you calculate the determinant of a 2 by 2 matrix, this 2 by 2 matrix A minus lambda I, when you calculate the determinant, the coefficient of lambda squared is going to be 1. And so this form is correct when you factor lambda 1 and lambda 2. You don't get some other constant out in front. Okay? So what does that tell you about the determinant of A? The determinant of A is the determinant of A minus 0I. So it's what you get by plugging 0 into the characteristic polynomial. And that's going to be 0 minus lambda 1 times 0 minus lambda 2. And that's going to be lambda 1 times lambda 2. So the determinant of A is the product of the eigenvalues of A. Let's put that in a box. Another fact that we'll need is what happens when you expand the characteristic polynomial. This is going to be equal to lambda squared minus lambda 1 plus lambda 2, lambda plus lambda 1, lambda 2. And we've seen that the characteristic polynomial of such a matrix is also equal to the characteristic polynomial is also equal to lambda lambda squared minus the trace minus a plus d lambda, right? The trace is a plus d, and then plus the determinant. So if you take these polynomials, they're the same. If you match the coefficients together, actually this is another way to see that lambda 1, lambda 2 equals AD minus BC. But in addition, you see that A plus D is equal to lambda 1 plus lambda 2. So also A plus D is lambda 1 plus lambda 2. That's the trace of the matrix, is the sum of the eigenvalues. So let's put that in the box also. Okay. Actually, we don't need... this part is just a parenthetical remark, that the sum of the entries is called the trace of the matrix. Okay, well, I'm going to use these two facts to find the criterion. So the criterion is this. If the determinant of A is positive and the top left entry is positive, then the matrix A is positive definite. Okay, why is this true? So we know that the determinant of A is lambda 1 times lambda 2, right? And we know that this is positive, so therefore lambda 1 and lambda 2 have the same sign. Well, if lambda 1 and lambda 2 are both positive, then A is positive definite. Now, why can't lambda 1 and lambda 2 be both negative? Lambda 1 and lambda 2 cannot be both negative. And the reason is because if they were, okay, then A plus D would be negative, because lambda 1 plus lambda 2 is equal to A plus D. Well, if A plus D is negative and A is positive, then D is negative. Right? I mean, if you have a positive number A and then you add some number and you get a negative number, then that number you added had to be negative. So D is negative, but okay, what would that mean? If you look at the determinant, AD minus BC, that's the determinant of A, that's equal to AD minus BC. If A is positive and D is negative, then AD is negative. Actually, C is equal to B, so this is actually B squared, right? So my matrix A is, I'm writing it like this. The determinant is AD minus B squared. This would be negative, and this is a contradiction, because we assumed that the determinant of A was positive. Okay, so this is a contradiction. So lambda 1 and lambda 2 are both positive. So that's how to tell if a matrix is positive definite. If the top left entry is positive and the determinant is positive, then your matrix is positive definite. The next statement is if you have a positive determinant and the top left entry is negative, then the matrix A is negative definite. Okay. So for instance, if you had something like -3, 1, 1, 5, right? This top left entry is negative, but the determinant is not positive. It's, let's change this 1 to be like, Let's see. Oh, well, now we see what's going on. We can't, if you try to take the determinant where you have a positive top left entry, a negative top left entry and a negative bottom right entry, this is going to have a negative determinant. Okay, so let's just explain why. So, because D must be negative, if the determinant is positive, and if D is negative, so you have something like this. If D is negative, then A plus D is negative, right? But A plus D is the sum of the eigenvalues, and these have to have the same sign if the determinant is positive. And so since lambda 1 and lambda 2 have the same sign, lambda 1 and lambda 2 are negative. So A is negative definite. And then I'll leave the third one as an exercise for you. If the determinant is negative, then the matrix A is indefinite. Okay, I'll let you think about why that's true. So this is a handy criterion for positive definite matrices. It's a quick way to tell if a matrix is positive definite, negative definite, or indefinite without having to actually calculate the eigenvalues. Okay, I have to go. Thanks for watching.